name is Manish Gupta, and in this video, I'm going to talk about multimodal persona-based generation of comic dialogues. This work is in collaboration with collaborators from IIT Delhi, Harsh, Aditya, and Professor Mosam. This work was also presented recently at ACL 2023. So let's get started. What is the comic dialogue generation problem? Right. So let me just straight get into the problem definition. So the task is next utterance generation for comics. So given a comic strip, as you see here, there is a comic, there is a conversation going on between these two cartoon characters. This is basically the ink pen comic, and the character is Tyr. And then there are some persona facts associated with this guy. So he's the Norse god of war, law and honor, and so on, right? And then there are a few frames for which you basically have visual inputs as well as you have the text inputs, right? All of those. And the idea is that in this next frame, basically in the fourth frame, you have to essentially guess what this guy would say, right? So what are the inputs? Well, inputs are all the frames before, all the frames inclusive of the current frame, right? All the visual inputs inclusive of the current frame. You also have all the utterances which have been spoken so far, and you have to essentially predict the next utterance, right? You also have as input the persona facts associated with the person for whom you have to predict the next utterance. So this is where this dialogue, this is where we contribute and we create a comic dialogue generation model. This is the gold response, of course, which is useful for training, and this is the response that our model generates. So if you think of it, you can pause the video and see in the entire context, the response that is generated by our model is reasonably apt. Right? So more formally, the inputs to as part of a problem are the conversation history with utterances, aligned sequence of visual scenes, and also persona facts for the comic character. And what we have to output, the expected output is the next utterance by the character. Um, of course, the broad goal is to be able to build multimodal dialogue systems such that, when you have multimodal inputs, image as well as text, how do you support conversations? How do you do the next utterance generation, right? But then in this work, we specifically focus on comic strips. There are awesome challenges. So, well, it's sort of difficult to incorporate multimodality in dialogue models. This is the first time that we did this, right? Multi-party dialogue. So in this particular strip, there are only two characters, but then in some other comic strips, there could be multiple characters. Personas. So each character has their own persona. So somehow we need to incorporate that also in dialogue generation. And lastly, humor. Comics are all about humor. Capturing humor in generative models is a very difficult task, and that makes this task difficult and challenging as well. So there's a lot of related work. There is work on dialogue generation. There's also related work in multimodal datasets for dialogue generation, right? So in dialogue generation, the field is very rich. There are models like DialogGPT, which is essentially a GPT-2 based decoder, which is pre-trained on Reddit conversations, and it makes it dialogue generation model. There's also work on Edge. There's also another work called Edge. So it allows for controlled response generation by conditioning on semantic frames of exemplar responses. So essentially, it sort of provides a structure to the conversation. It's sort of given a test conversation, it tries to figure out which structure fits the best, and under that structure tries to predict the next response. Right? BERT over BERT. So this one essentially it has a shared BERT encoder, but has two task-specific decoders, one for dialogue generation and the other for consistency understanding of the generated utterance. The fourth one is PersonaGPT, and this one is basically a GPT-2 fine-tuned model, but with persona information also associated. So it is actually fine-tuned on persona chat dataset. Okay. So this is existing work in the dialogue generation field, and there is a lot more work. So I really motivate you to look at other papers also in the dialogue generation area. Right. More recently, people have started working on multimodal datasets for dialogue generation. So comics is one such dataset. However, people have not really leveraged any of the interesting dialogue generation kind of models on top of this comics dataset. It contains scanned images of comic strips, but they are not but they do not have manually extracted transcripts information. They have just done OCR, and they themselves claim that the OCR basically leads to a lot of inaccuracies, and therefore the dataset cannot be really used for dialogue generation. Persona chat dataset. So it basically contains conversations between two agents and their corresponding persona facts, but doesn't have images. So it's multimodal in the sense that it has more information about personas, but does not have any images. There are other datasets like image chat, photo chat, visual dialogue, and so on. Now, however, they are all conversations in the context of one image. So it does not have like multiple images So it does not have this concept of co-evolving modalities. It just has one image, and then there is a text dialogue in the context of that image. So that is how our work is very different from the existing pieces of work. Now, to be able to do these things, we essentially came up with this new dataset called as Comset. In this dataset, there are 13. We first gather data about 13 comics from Go Comics. Each comic strip contains transcription and an image. So it has a transcript and also an image. We deduplicate these comics. We remove duplicated, repeated comics, right? We do several cleaning steps so as to get this data set. I'll discuss some of these on this slide and some of the remaining ones on the next slide. So once we have these transcripts, we need to parse them so as to structure them out. So for example, transcripts are free-flowing text. In some cases, it's basically combined. It's a combination of speaker, the character, and the utterance. So both of those have to be nicely separated out. And the way we do that is to first get a list of popular comic characters in any particular comic, and then match them with person entities in the transcripts. Now, many of those tail characters cannot be matched nicely, and therefore we consider them in a single bucket, others bucket, which contribute about 17% of those tail characters. Sometimes characters also do not have names and therefore cannot be really identified as person entities. So in those cases, we basically take those non-named entity speakers and specifically identify them as persona or characters, speakers or characters, right? Like man, woman, stranger, voice, noise, sound. So those are some of those which are not detected by as person entities, but we still consider them as proper characters, right? Now, sometimes there are also spelling mistakes in these transcripts for character names, and we use edit distance to handle those spelling mistakes. Now, especially in one particular comic, there were like 4 different things which were present in these freeform transcripts. They included the character name, of course, as usual. They also contained the utterance as usual, as already previously mentioned. But further, they also contained the action or attribute phrase, and then the speaking verb. Right. So an example is as follows. Bucky is holding Smacky and says XYZ. Right. So here Bucky is the character, is holding is basically the action or attribute phrase, is holding Smacky, and then says is basically the speaking verb. Now the speaking verb could be says, replies, yells, asks, proclaims, and so on. There could be so many other such verbs. So essentially, we also built various heuristics based on part of speech tagging, named entity recognition, dependency parsing, so as to be able to nicely parse these 4 different parts which are present in these freeform transcripts and get the right things out. So specifically, we are interested in character and the utterance. Right. Now, further on the panels side, on the visual part, right? So we have multiple panels. Each comic strip essentially has several panels and utterances across those panels. So to be able to extract these panels out, so first step was to really take a strip and get the panels, get those boxes out. So we essentially leveraged faster RCN and object detector with ResNet 50 backbone. We manually annotated some 500 panel bounding boxes, and then we observed that this faster RCN worked really well. So as you can see, it has nicely extracted those panels as frames given the comic strips. The third step as part of pre-processing was to actually do dialog text detection and masking. So you have the panels, that's great, but I really want these dialog text detected nicely, right? So this was useful in 2 parts. First, it was useful in the next step that we'll talk about, multimodal alignment. It was also useful because we wanted to mask them out for the frame for which we want to actually predict, because we don't want the visual aspect of that frame to also leak out the utterance that we want to actually predict, right? So we use easy OCR to extract the bounding box and the text for each segment from each segmented panel. Now we fill the bounding box with random noise. So as you see, it's basically filled with random colors so as to not get biased towards a particular color. Okay. The fourth step is basically multimodal alignment. So we have the OCR text coming from the panels. We also have utterances coming from transcripts, which I discussed on the previous slide. So we use the simple Levenshtein distance or sort of edit distance based similarity score so as to match these. So thus, we basically get the best matching panel for every utterance from the transcript. And then, sometimes it happens that, typically from a transcript, it's sort of monotonically increasing in that senses. So you also would like to have monotonically increasing sequence number of the panel associated with every sentence in the transcript. However, that does not happen. And to make that happen in like 2 to 3% cases, we basically just use a dynamic programming sort of algorithm to fix this non-monotonicity and have finally a monotonically increasing sequence associated with the different sentences, sequence sentences in the transcript. Now, the next step is persona fact generation. So we have already identified popular characters for every comic. We essentially go ahead and manually extract, in some cases, persona facts associated with every character. In many cases, we are able to find fan websites, and then we could basically extract persona facts about those characters from those fan websites. Once we have the data set, we have data set for about 13 comics, and we divide it into train comics and test comics. So 8 seen comics and 5 unseen comics. And then further within the scene set, we basically split it into 70, 10, 20 so as to also do evaluation on the scene set specifically. So this is how the overall statistics of the Comset dataset look like. So we have about 3 characters per strip. So it's really a multi-party dataset, right? We have about 16 tokens on average per dialogue. We have 57 persona facts per comic. So I mean, of course, this is across different characters. So for particular character, we have about 7 persona facts per character. For every utterance, there's slightly less than 1 image. So per utterance, so basically 2/3. So essentially, the way to think of it is like for every 3 utterances, there are like 2 images on average, right? And the data set is really large number of utterances overall and a really large number of panels spanning over around 54,000 strips. Right. So that's that. And overall, the dataset contains 202 characters. So the dataset is pretty large in that sense, given those stats. Now, we did so many pre-processing steps, as I discussed on the previous few slides: parsing transcripts, panel segmentation, text masking, multimodal alignment. Each of them actually comes up. They're all automated, so some of them have some inaccuracies. Overall, however, on a set of about 100 to 200 examples, we evaluated that our end-to-end accuracy is about 92%. Right. So here are more details about each of those 13 comic strips. So, if you really are interested in each of those details, you can pause the video and look at them in more detail. Okay. Now, what do we do with this data set? We have to come up with a model which can incorporate this persona aspect and also in some ways incorporate the text and the image aspect, right? So this is the model that we come up with. Remember, the task is next utterance prediction, right? So basically the input is the output is utterance at time t, and the input is a comic strip with conversation history up to time t-1, and also an aligned sequence of images up to time t, right? We also have the persona facts associated with the character for which we want to come up with the output, right? We limit the history to 5. So essentially, we basically say that, hey, we do not want to care about more than 5 utterances, so we limit the history to past 5. Okay. So as baseline models, we consider the language model only models, DialogGPT and Edge, which do not incorporate any visual information or any persona information. But we also consider LM plus persona, so language plus persona. So which basically PersonaGPT and Bob kind of models, which basically generate persona consistent responses, right? So therefore, we expect PersonaGPT and Bob to be better than DialogGPT and Edge because our dataset comics basically has this persona aspect anyway, right? We fine tune these baselines on the Comset train part, the train part of the concept of a Comset dataset, right? So what does our model look like? So remember, our model has to be multimodal in nature, should incorporate text and images. It should be able to incorporate persona as well, and generate persona consistent responses. So that's how our model looks like. So our model basically takes persona. It basically takes text aspects, and then there's a separator, and then there is an image, and then there are multiple text parts individually separated by an end of text token. And then there is another image, and then there is another text part, and then there is another image and text parts, and so on, right? And then there's a prompt to basically say that, hey, I want to generate response for tail. Okay. Now there is a MME module, multimodal embedding module, which basically does embedding. So for the text part, essentially we have the text embedding module, which is a 12-layer PersonaGPT base. For the image part, we have a visual embedding module plus this linear projection. So visual embedding model is essentially a 12-layer clip VIT vision encoder, and the linear projection essentially just tries to project these d-sized embeddings to n-cross-d embeddings, and ensures that the image can be represented as n different tokens, each of the embedding size that the transformer decoder can accept, right? So, and then the MME model, of course, interleaves the text and the vision parts appropriately, such that the text part of every frame comes first, and then the image frame part of that frame comes, and so on. So this continues until we have the input, right? So the decoder is essentially also a 12-layer transformer decoder. It's essentially initialized using PersonaGPT base, so that it basically has this persona concepts already, right? And it's fine-tuned end to end. Now, of course, we prepend the persona part. The P part is the persona part right in the beginning, so that that also is a part of the input. Okay. So how do the results look like? Well, these are the results on our seen part as well as on the unseen part of the data set. So we compare 4 baseline models, the 2 language-only models, and the other 2 persona-based plus language-based models, right? So notice that the size of our model is 213 million parameters compared to, let's say, BERT over BERT model, which is larger. So we report these different metrics: perplexity, so lower the better, blurt, mod, precision, recall, and F1, right? So those are all the different metrics. Now, as you can observe, MPDIALOG is actually better compared to all the other baselines, language model only baselines or persona-based baselines, both for the seen as well as the unseen data set. Right? Language model only baselines, DialogGPT and Edge, the problem is that they cannot generate coherent responses. So if you look at them, their perplexity is much higher in that senses. Perplexity is much higher. And the mod scores are much lower, right? Mod scores typically, let's say 0.807. It's pretty low compared to the best scores that we obtain. Right? Adding persona information does help reduce the perplexity. So if you look at Persona GPT, well, the perplexity is significantly lower. Lower is better. So this is really good, right? Persona GPT with respect to perplexity. However, the best model is clearly our model, where our model MPDIALOG actually incorporates the language model information plus the persona information plus the visual information compared to the other baselines, right? So we also show here comic-wise quantitative analysis. So the idea is this is for seen and unseen data sets, and this is comic-wise. You actually observe the metrics being shown here: blurt, mod, and perplexity. Remember, perplexity lower the better. For the other 2 metrics, higher the better. And then we have results shown for all the 5 methods: 4 for our four for the baselines, and then the last column is our method. Right. So what you observe is that for most comics across all the 3 metrics, we observe that MPDIALOG, our method, gives you the best results. However, for one metric, for one comic, so please this particular comic for which our method somehow does not perform better on any of the metrics. So we try to understand why this is what is the reason behind this. So we observe that the Cleats comic focuses on the relationships between the characters a lot, their sportsmanship, and the challenges of being part of a team. Images do not play a major role in this particular comic. So images do not contain much additional information, and therefore we sort of believe that that is the reason why our model MPDIALOG, which basically has this extra capability of handling images, does not really perform that well. We also perform some qualitative analysis. So here is an example of a comic from a comic strip from Garfield, and there are persona facts about Arlene. So Arlene, right? And we have to basically guess what Arlene would say in this particular comic, right? In this strip. So the context is, Garfield says here, right, in the previous frame: I adore you, I worship you, I love you more than life itself, I can't live without you. And the good response, Arlene just says, Garfield, right? So there are all these various baselines, responses that you see here, and this is a response from our model, right? So what we observe is that responses for other language generation, language only models, as well as other models like DialogGPT. So either the responses are too banal, too usualish kind of, too simplistic kind of responses, right? Or they're completely nonsensical, as you see here. Yes, PersonaGPT does come up with some reasonable response, but our MPDIALOG response is much better. Now, yes, I mean, one thing to observe is that, yes, our MPDIALOG work sort of comes up with longer responses than expected. In comics, comics typically expect much shorter responses, but that's more future work. How do you reduce the length of this of these responses and still bring them under, still keep them reasonably nice and awesome, right? So one other experiment that we did to come up with the qualitative analysis from a model is to basically look at the character level train vocabulary distribution, and then look at the character level vocabulary distribution of the generated outputs from these models. And we observed that the KL divergence between these character level vocabulary distributions between the actual training set and the generations from various models, in MPDIALOG, it was much lower. So KL divergence is a distance metric, so lower is better. And we observe that in what we observed is that the character level vocabulary distribution, which is generated by our model, is very close to what was there in the training set. Thereby sort of we can conclude that our model basically generates consistent responses. We also got human evaluation done of the responses generated by various models on 5 different parameters. So they include fluency, engagingness, dialogue consistency, scene consistency, which are defined here. So for example, in terms of fluency, we want to measure how easy it is to understand the response. Engagingness basically measures how interesting and unique the response is. Dialogue or scene consistency measures how consistent is the response with respect to the dialogue or the image history. Persona detection is a special metric. Here we sort of measure that given the persona facts of the two characters, which persona does the response match to. So we took the actual character and some random character, and we just asked, hey, which character does the persona match with, right? And we got all of them manually labeled. So what you observe is that on most metrics, MPDIALOG performs reasonably well. Even on cases where it does not perform that well, it is close to the best model, close to the best model. Okay, so in conclusion, in this video, I talked about comic dialogue generation. Specifically, we contribute a new data set called as Comset, which is a comics data set with about 54,000 strips and 200 plus personas. We also contribute a new model called as MPDIALOG, which is a persona-based multimodal dialogue generation model. It's sort of a baseline, as we call it. I mean, and we hope that people will use our data set to come up with even stronger models in the future. Our experiment showed that leveraging multimodality and persona orientation improves the quality of dialogues. It is at least better compared to those dialogue models which do not really incorporate persona information at all or image information at all. Right. In the future, the goal is to make the responses contextually coherent. So, these responses are still not as coherent as we would like them to be. The responses are also long in nature. We would love them to be slightly brief and shorter, right? In this particular work, we did not evaluate the humorous nature of these responses. Our initial experiment showed that coming up with humor is very complicated. So future work, we also want to focus on how to generate humorous responses. Lastly, exploring generation of next utterances jointly with panel images. In this work, we basically is focused on generation of text, the utterance text, but in the future, we also want to focus on jointly trying to generate panel images along with the utterances, given various image generation models that have shown really awesome results like stable diffusion, etc. Right. So hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.